All right, so this is how we get numbers, okay? Because the universe literally programs them. All right, so all we have is a galactic year. Okay, we know a galactic year is 250 million years roughly. Okay, technically it is 250 million years exactly, more or less exactly on our scale. All right, we don't have an astronomical week or an interstellar day, but they exist. Okay, and that's where we're losing some measurements in the universe. Okay, so an interstellar day is 2.25 billion years, okay? So when you divide 13.5 into 6, you get 2.25, all right? The universe is 13.7, but the 6th day ended 200 million years ago, okay, technically. And we're 200 million years. We're 11.25% into the 7th day, technically, okay? I'm going to diverge. Anyway, all right. So, an astronomical week, okay? An astronomical week is 750 million years. Now, this is actually an Earth eon, okay? An epoch, okay? But we're not recognizing the significance here because 3 galactic years is 1 astronomical week, okay? When it makes 3 revolutions around the galaxy, all right? When our solar system or our sun makes 3 revolutions around the galaxy, that's an astronomical week. All right? And when you have 3 astronomical weeks, you get 1 interstellar day, which is 2.25 billion years. You see what I'm saying? Okay, so these are measurements that are actually there, but we're not recognizing them. We only see a galactic year, but we see an Earth eon, but we're not recognizing the significance of an astronomical week and an Earth eon, because even those can be divided into 6. All right, so look, you have the interstellar day, the astronomical week, and the galactic year. All right, so 1 interstellar day, 2 interstellar day, 3 interstellar day, 4 interstellar day. All right, that would be 3 astronomical weeks, 6 astronomical weeks, 9 astronomical weeks, 12 astronomical weeks, and so on and so forth. All right, this right here, 9, 18, 27, 36, 45, 54, and so on. All right, then when you go down this way, you get the difference here. You got 2, 6, 4, 12. All right. Now look here. You get 2, 4, 6, 8, 10, 12, 6, 12, 18, 24, 30, 36, and it just keeps going. Okay? So the numbers, the universe is programming mathematics, okay, through astronomical evolution. All right, so then you have 6 Earth epochs. You have 750 million years. Divide that in 6 you multiply that times 6, you get 4.5 billion, okay? So that's 4.5 billion years. That's the age of the planet, okay? So Earth, when you do the 3, 6, 9 astronomical weeks here, you got Earth is 18 galactic years old. It's 6 astronomical weeks old. And carbon-based life forms, 6, and nitrogen organic compounds, 6 and 7. There's another significance between the 6 and the 7, okay? The 6th day and the 7th day, all right? Because carbon-based life forms, carbon-nitrogen-based life forms, that's the organic compounds that created everything on Earth. I mean, the life, okay? Nitrogen, amino acids, stuff like that is based on carbon and nitrogen. Okay, so Earth is 4.5 billion years old, all right? That's 2 interstellar days, okay? It's divided in the 2 interstellar days right here, all right? So you have your astronomical weeks, 3, 6, 9, 12, 15, 18, all right? Now, in these epochs here, you have the Hadean, the Arcanian, Proterozoic, and Phanerozoic, all right? And those are divided up. See, this is when prokaryotes ultimately evolve, and eventually the eukaryotes will evolve. But prokaryotes evolved a lot sooner than we thought, and according to this, it was even a lot sooner than that. You see, an interstellar day, an Earth day, whenever Earth forms, relativity to that planet begins, okay? So Earth has a day of 750 million years, which is an Earth epoch, rather than 2.25 billion, because now the relativity scale has changed. Now we have fundamental relativity since the planet formed and our fundamental measurements began, okay? And that's this area right here, okay? From right here over. And this is when the prokaryotes and eukaryotes evolved, okay? So that would be from here over. That was when the relativity changed, the scale. Fundamental relativity of 750 million years becomes a fundamental measurement for a day. But it's shared. See, it's shared actually on the 5th day. See, on an interstellar day, this is when Earth begins to pretty much, it forms. The planet begins to form from an accretion disk, and fundamental relativity begins, and so on and so forth. But see how it transitions from an interstellar day into an astronomical week right here, because the fundamental relativity changes. And then when it goes smaller, you get galactic years. You see what I'm saying? You basically have the macro and the neutral scales. You know, the macrocosm and the microcosm, or fundamental relativity. And then once you get to the prokaryotes, you have the microcosm. You know, you get cells and small organisms, tiny organisms, you know. But it all derives from tiny quantum energy anyway, you know. The micro gives birth to the macro, which through reversion gives birth to fundamental relativity. And I'll show you how that goes. All right, see, the quantum micro scale is going to form a singularity, which is going to birth the macro, or the universe, okay? But through that reversion, fundamental relativity, or through the decay, fundamental relativity is formed, okay? Fundamental relativity, what we measure in our universe, can begin through a decay process. Everything is about decay. The whole universe decays. Even a void decays into something, which is alpha decay, nuclear energy. And then that decays in through beta decay. So you got alpha, beta. Once you merge these two, fusion, thermonuclear fusion, from nuclear and electric energy, then the singularity forms. And this is the growth between these, which is omega. I'm just throwing that out there. Okay, it's Greek. It really is. I mean, when when everything reduces, I mean, I think that's where the term comes from. Well, it's all Greek to me. Technically, it has a root. It's talking about something specific. So the microcosm, quarks. Okay, it begins with quarks. You know, absolute zero. Now it's at a boson-sun condensate because it's cold. All right, the void is decaying, alpha decay. Okay, and an alpha particle is identical to a helium-4 nuclei. And helium is the only particle that we can turn into boson-sun condensate. And this is why, okay, through alpha. All right, now it's nuclear energy. It's going to become protons and neutrons, okay? And that's a helium-4 nuclei, 2 protons, 2 neutrons. All right, so you got quarks, which ultimately form the singularity. It inflates, it forms a photosphere. It does everything that a star would do, but on a quantum scale. Okay, this is pre-atomic. Okay, atoms don't form yet. This is when atoms are going to start forming. This is when the constituents of the energy, you know, it gains color charge and what would be considered Coulomb's law. You know, because you're giving it kinetic energy. You're getting, like, imagine this: you take a balloon, you rub it in your hair. All right, then you take paper, chopped up piece of paper, and you put it over the balloon. The paper is going to sit there and float and hover around because of the static charge that the balloon has. Okay, this is pretty much what's going to happen to these quarks. Okay, they have no color charge yet. They're cold. They're at a boson-sun condensate. They haven't heated up yet. So it's like a holy superatom. You know, it has no color charge yet. So it literally gains this charge, this kinetic energy, which allows electrons to be able to hover, essentially. But it's all a part of angular momentum. And I'm going to get ahead of myself. I'm just going to say that centripetal force is gravity, and angular momentum or centrifugal force is anti-gravity. Okay? And it starts on a microcosmic scale with the color charge. That's angular momentum. Then you got an atom. That's angular momentum. You got galaxies. They spin. Everything spins. Angular momentum. You got solar systems. They spin around the sun. Angular momentum. The moon goes around the planet, angular momentum. If none of this had angular momentum, everything would collapse. Gravity would literally collapse everything. Gravity is the strongest force, technically. It is. But we see it as the weakest force because it's harder to understand, but we're not understanding fundamentally it begins on a quantum scale. And we talk, well, gravitons, we haven't observed them. Technically we have. It's not a particle, it's a force. you know. You're not going to observe a graviton because it's not going to be a graviton, you know. It's a graviforce. I'm just saying. It's the angular momentum, the color charge that quarks have, and then the electrical charge that electrons have. I mean, they're traveling at 4.5 or 4.9 million miles per hour, roughly. So they're not going to collapse. You know, they got a lot of angular momentum. So if I'm guessing, I'm theorizing that if you can literally take matter and accelerate it to at least 4.9 to at least 5 million miles per hour, 6 million miles per hour, then it would literally fall apart. The momentum would literally cause the atom to fall apart. The electron would fall out of orbit. The color charge would completely turn into Bose-Einstein condensate. I mean, it would all decay again. But the micro is going to give birth to the macro. And through this decay process here, the reversion or fundamental relativity begins. You see what I'm saying? And then over time, decay, it's going to reduce back into carbon, ashes. It's going to reduce back to cold, ashes to ashes, dust to dust. Because it is a carbon-based life form in the first place. Because these quarks, these point particles, these micronova, are carbon-based. Okay, because they're micronova. They're flashes. They're points. They're point particles. They're micronuclear energy. Okay? So they're already based off of a carbon ash, more or less. So whenever this singularity ends up forming, it's analogous to a zygote. Okay? A human zygote, or any animal, any eukaryote out there. You got the nuclear and the electric energy, the mitochondria and the nuclear. Okay, mitochondrial energy inside cells is electrical energy. It sends electrical signals, uses ATP to connect with other cells, and sends signals all throughout the body. Okay, so it's an electrical product, and we can observe this biologically. In the universe, even though it's the universe and we see all these planets floating around and all this stuff, doesn't mean that it has no purpose. Even if you went inside the human brain and you saw all this weird stuff happening, you wouldn't understand what it is. You'd see all kinds of just weird stuff happening. But then when you come out of that and look on the inside, you think outside the box, you know, and look in, then you'll see, oh, okay, so it made up an organism. You know, it made up a larger product. So when you see all this stuff, these random happenings, I call it random happenings. You got random happenings happening in space. It's like you have random happenings going on in your body right now. The planet has random happenings going on all over it. But it's all living animation. You know, it's animated. And animation is life. You know? And you don't have to think of it as like it eats and sleeps and all that stuff, you know? You just got to think of it as it's not emotionless. It's not without animation. You know, it's not just without. It is, you know. So when this happens, so you're going to get the reversion here. The energy converts to a lower state, which is matter. And matter decays and turns to ash, cooling back to near absolute zero. See, near absolute zero can't happen inside our universe because when the Big Bang happened, it's a galactic nebula, okay? C equals mc squared. All right. The mass times the speed of light squared. Okay. Squared always exists. That's the area of space. Squared is, was, and always will be. All right. And that's where the concept of the cube or the square in space comes from. Because square always exists. You see what I'm saying? Energy. Okay. The energy of the Big Bang is going to be the universe. The universe is the product. That's going to be the energy. Okay. So you have the mass of the singularity times the speed of light squared. The speed of light in an area, okay, equals the universe. You see what I'm saying? The mass of this singularity, because when it formed, I mean, literally, it's every atom in the universe. It's every piece of everything in the universe in this singularity. But relative to space, which already exists, see, space, time, and matter didn't form in the Big Bang. Okay, space already existed. Or how do you have an area? Where's what you know? If they say this is tiny, then what's it tiny to? It's got to be relative to something because tiny is a measurement of size. That means it has to be relative to something else to be tiny. And they're telling you right there, but they're not telling you that space already pre-exists. You see what I'm saying? This pokes holes all in the Big Bang Theory because the area of space has to exist or the singularity can't exist at all. And plus, time cannot exist if you have no measurement. You can't measure the beginning of space at all You can't measure the ending of space because technically you can't apply time to space. So space-time technically is an illusion. What it is, it's matter-time, or it's timeless space, until you add matter. Once matter is relative to space, then you can have time. Because, say you just have infinity. Just a blank piece of paper. That's dark space forever. No light, no nothing. Cold is, just minus 470 degrees, And then, so, how are you going to measure that? When are you going to start time? Well, whenever the matter forms. Whenever you get the matter, boom, oh, well, now we can start space. Space-time! So it's timeless space until space-time forms, because the matter forms. So it's timeless space plus matter equals space-time. And look, in space you have infinite dimensions because of the degrees of freedom. Now there's no up and down in space, because any degree that you have anything is technically right side up, and because most generally anything in space is spherical in nature, So there is no up or down. But you can actually grasp 12 if you consider squared with 2 axes, like I explained in a couple of videos, It's the area of space, the Higgs field, so to speak. But when this forms a universe and time propagates, that's the dark energy. It's nebulatic. That means it's going to form a nebula. Okay, it's a macro nebula. We live in a galactic nebula, just like a Crab nebula happens. Crab nebula is microscopic compared to the galactic nebula we live in, which is the universe. You see what I'm saying? It's the same thing over and over. It just happens on larger and smaller scales. And to grasp it, you have to understand high-speed and slow-speed photography, because that helps us grasp. When you look at an explosion, thousands of frames per second, you'll understand the singularity a lot better, how the protolight spread. Because that flash, even at those frames, you still only see a flash. And that's the layout of the universe. That's the protolight. That flash laid out the grounds for the universe in a neutrino kind of way. Okay? Laid out the static neutrino format, more or less. All right. So, since you have this time and dark energy, now you can't technically travel back in time because you can't rewind these galaxies back to the time that they were, say, in 1960-something. Like, say, in 1960-something, they were all back here, and then, 30, 40 years later, they're all spread out a little bit further. You can't go back in time because you can't rewind the universe back into that time. You see what I'm saying? You can't actually rewind time. You can't travel back in time. You can travel in time in the future, technically, through time dilation. Because if you travel close to the speed of light, and this is just theoretical, because the measurements work, the math works, but we just can't achieve that kind of speed, And that's the only way we can really even travel through time, is if we can actually travel very fast, close to the speed of light, and we'll only be able to travel into the future, and once it's done, it's done. We can't rewind it, so we'd have to be very meticulous. So, this is just what I've figured out. If anybody can debunk it, that's cool. If anybody says, hey, man, I got something to add to it, hey, that's cool. Awesome, thanks, we can help each other, you know what I'm saying? I'm just trying to help people understand something it's fundamental that we're not seeing. There's a lot of fundamental stuff that we're not seeing that it should be common knowledge. And if it was common knowledge, I think there'd be a lot less fighting in the world because, people have more understanding. You know what I'm saying? Because if you have all the facts, then you have free choice. If you don't have all the facts, then you're being led. You see what I'm saying? You're led to believe something. But if you're given all the facts, then you can choose to either acknowledge them or not accept them or whatever, or you can accept them, It's your choice. But most generally, people will accept facts. You see what I'm saying? They just need to be taught them. And I'm saying they're all out there in our faces. It's just there's so much chaos in the world, it's hard to sit down and actually start looking into it. You know what I'm saying?